All right. So we're going to go over the Chapter 6 study guide. Guess what? We're doing metallic bonding today. We're going to do it with that study guide. There's not a ton of information to know about metallic bonding, and then we'll move on to ion dot structures. And again, if you guys are listening to me, I'm really trying to help you out and cue you into the kinds of questions that are going to show up on your quiz on Thursday, because your quiz on Thursday is going to be matching ionic, metallic, covalent, that you'll want to make sure that you're matching stuff. So especially now that I get into metallic, I'll compare, like, oh, ionic would have been this, but metallic would be this, right, for your quiz. So with that, let's start off on the left side of the front, which is fill in the blank and some true false, I believe. Yep. So we'll get this whole side in a minute. I'll scroll down halfway through. Oh, forgot to scroll, of course. Here, let's get the rest of that true false up. Come on. All right, so there's the bottom of that side. All right, good to go to the next side. True false. Okay. All right, then we got our multiple choice. So a bunch of multiple choice here. Here's 18 through 22. All right, then let's get the bottom half of that side. All right, then go into the back, right? So a couple more multiple choice and then some matching of sorts, I guess. Just pick the right one. It, and then the bottom half with some more true false. There we go. All right, so any questions up to that point for the ionic bonding? Good. Okay, I'm actually going to do the last section with you. That's going to be our notes on metallic bonding, is that last half of that last page. So let's talk about metallic bonding. Everything we need to know is going to be on this paper. So in metallic bonding occurs between metals. Metallic bonding, metals. In contrast, ionic bonding was between a metal and a nonmetal. Okay? All right, in metallic bonding, we describe this whole process of metallic bonding as the electron C model. The electron C model. What happens in the electron C model is that your metallic atoms all come together and their valence orbitals overlap. There is no overlapping in ionic bonding of orbitals. There is overlapping of orbitals in metallic bonding. When those orbitals overlap, all of the valence electrons that used to be stuck with one atom are now free to move to any other atom that has its orbital overlapped with it, right? And that's what we call, or here, it's always the valence electrons, because that's where the overlapping is occurring. And those are the electrons that we call the delocalized electrons. That's a very big vocab word for metallic bonding. They have delocalized electrons. What does that mean that they're delocalized? That means they can move from atom to atom. Free to move from atom to atom. They don't have to stay local. They don't have to stay with the atom that they originated with. And they're not even just stuck between two atoms, right? They're free to move to any of the atoms that are part of that metallic structure, right? Those are delocalized electrons. In an ionic bond, electrons were transferred, and it happened, and then it was done. There was no going back. The electrons went one direction from the metal to the nonmetal, and then that was the end of the story. So that's going to be a difference here, that in metallic bonding, we would say that the metals do not completely lose their electron. Let's get that. Metallic metals do not completely lose electrons. As they do in ionic solids. Because while this delocalized electron is out there swimming, I use that analogy, the electron C model. We think of all of the overlapping orbitals as creating like an ocean, a sea that they can swim in. They can still come back. They're not like prohibited from going back. They're just out swimming and playing. And sometimes they come back around, hi mom, hi dad, and then they go back out again, moving around through those overlapping orbitals. But in an ionic solid, no, it's a transfer. Metal gives up that electron. Bye. You now have custody. No longer my problem. I will never see that electron ever again. Question? Yeah. Yep. Okay. So that's kind of the idea behind the electron C model. I would also say that metals don't exist as molecules. You can put a note there, no molecules. If anything, they're more similar to ionic compounds in the fact that there's a three-dimensional repeating pattern, right? But instead of cations and anions, we just say that it is made up of metal cations. How do I know they're cations? Well, guys, those delocalized electrons, they used to be the valence electrons of the atom, and now they're off. So while it's not a transfer, you can think of that metal atom has lost an electron that's off swimming. So we know it's a cation because it has a positive charge, and it's because its valence electron is now part of this group of delocalized electrons that are just off roaming through the crystal. It might seem weird to call a metal a crystal. It's just about the arrangement of the atoms. There's a regular pattern to it. So, what is keeping everything together? Why is everything sticking to each other? Remember, it's always about opposite charges attracting. All of our bonds, opposite charges attracting. What changes is, what are those things? So in the case of a metallic bond, we would say it's the attraction of the negative delocalized electrons. And I'm going to write the word out just for clarity, the positive cations. And so I just want to point out, positive and negative charges are attracting. But it's negative delocalized electrons and positive cations. In contrast, in an ionic bond, remember, it's positive cations and negative anions. That's what's attracting to keep everything together in the ionic compound. So keep those straight. This is delocalized electrons and cations. Ionic bonding was cations and anions. Those are the opposite charges attracting. Here, no molecules, that there is an overlap, electron not completely transferred, and definitely those delocalized electrons, a key aspect to the entire electron C model. So let's take a little closer look at that, the electron C model. So here we're going to look at an atom of potassium. So here are 6 different atoms of potassium. Let me play a little bit longer. And they're trying to represent the electronic structure. There's the electron configuration at the top, and they're using a Bohr, like circular orbit model, not exact, but it's going to get its point across. So we have 19 yellow electrons and then a red nucleus. For simplification, we're going to take the first 3 energy levels, and we're going to make them into these little pink spheres. So the pink sphere now is the nucleus and the first 3 energy levels, and all that we've left is this 4th energy level, this 4s1 valence electron. Right? Because we don't need to know any detail about what's going on with the first 3 energy levels. So 4th energy level, that's still this ring with that 1 yellow dot, and then now the pink sphere, that's everything else. Okay, so when we have metallic bonding, that 4th energy level, they're all going to overlap. They don't grow like in the animation. They would just get closer to each other. They're just lazy to make that happen. But do we see now all of this yellow blob? That's all overlapping orbitals. That's creating the ocean, the sea. Because think of this in 3 dimensions, right? Once that overlap occurs, watch the yellow dots. They now can go anywhere. They're free to move anywhere within that overlapping system, right? And if I pause at different times, they could be anywhere. See, there's 2 of them right here, 1 right here, none right there. They could be anywhere at any given time. There's no rhyme or reason as to why they're in any particular spot. They're just doing their crazy electron thing. That's our C of mobile electrons, or your delocalized electrons. And then the sphere things, that's your cation, your positively charged cation that's missing the 1 valence electron that's now off swimming somewhere else. So that's a visualization of the electron C model. And there we go. So questions right now on the electron C model. All right, so then let's finish up with the properties. Okay, I was a little shocked. We did properties of metals last unit, but yet some people wrote, no, they're not malleable. I'm like, all right. I wonder how you did on that part of your test. So let's go quick first and just get the yes or no's. Malleable, yes. Brittle, no. You can't be both. You're one or the other, either malleable or brittle. Lustrous, yes. If you didn't know what that word means, that's a fancy word for saying you're shiny. Now for the melting and boiling points, I don't remember exactly what your textbook says, but I'm going to tell you, as far as I'm concerned for my test, they're variable. I would never say that they're the highest or the lowest. It depends on the metal. So they're always going to be somewhere in the middle. By contrast, remember, ionic compounds, they have the highest melting and boiling points because they are the strongest bonds. Also remember, ionic compounds were brittle, not malleable. We're going to come back to that. All right, ductile, yes. Poor conductor of heat, no. Good conductor of electricity, yes. Remember, ionic compounds, they can only conduct electricity when melted or dissolved in water. Yeah. All right, so now let's go back and hit on some of these yeses because there was supposed to be a little explanation that went with those. All right, I'm going to start first with the lustrous. I don't like this one, but it does come back to the delocalized electrons. These delocalized electrons, when they're running around, they can absorb and emit photons of light, and that's what you see as the shininess. Delocalized electrons absorb/emit photons. We don't have delocalized electrons in any other type of bonding. That's why those guys aren't shiny. All right, so let's go back to the malleable. And I want to review what's going on with an ionic compound so you can understand how the metal's going to be different. If you guys remember with the ionic compound, if you hit the ionic compound strong enough, you could shift the crystal lattice so that cations were right next to each other and anions were right next to each other, and that was bad news because like charges repel. That repulsion is what pushes the entire compound apart. That's why it shatters and breaks. Brittle, correct? When I think of a metal, when I hit a metal hard enough, what's going to happen is I'm going to move around these cations because they are what's making up the lattice. But it's not the cations being near each other that's good or bad. What we need is we need the attraction between the positive cations and the negative delocalized electrons. And guess what? Those delocalized electrons can move wherever they need to. So you never have to worry about getting a situation where you have too many like charges lining up because the delocalized electrons can go wherever they need to maintain the necessary attraction. That's kind of the, I don't want to say flexibility, but it's kind of like the flexibility. This lattice is not locked into a specific arrangement. It is able to be shifted around, and the delocalized electrons can always move to accommodate the shifts in the cation. Okay? So that's going to lead to the malleability of your metals. So what we can say is delocalized electrons shift to accommodate movement of cations. And so why does it matter that they shift to do that? That means that you can maintain the attraction that is the entire basis for the metallic bond the entire time. That attraction between negative delocalized electrons and positive cations. Even if the cations move around because you hit them, the delocalized electrons can always move anyways. You don't even have to hit them to do that. So you're going to maintain that metallic bond without worry. So for ductility, I'm just going to say C number 7 because it's the exact same issue, except in ductility you're stretching it into a wire as opposed to pounding it into a sheet, but it still is movement of the cations based on you applying a force. And hey, no problem. Delocalized electrons roll with it. They'll fill in and move wherever they need to keep the attractions. So last one. Good conductor of electricity and heat for that matter for the same reason. If you guys remember, in order to conduct electricity, there were 2 requirements. Requirement number 1, anybody remember? You need charged particles, and those charged particles need to be able to move. You need mobile charges, right? And so that's why we had to melt or dissolve our ionic compound because they had charges that were locked in place. But mobile charges. Oh, let's think about that with the metal. Do we have any charged things that are free to move? What are they called? Which ones? Delocalized electrons. Guys, by definition, that's what they are. Charged particles that are moving. So absolutely, they are going to be great conductors of electricity because delocalized electrons are mobile charges. And if you have mobile charges, you can conduct a current. That's also the reason for a good conductor of heat as well, the delocalized electrons. Hey, do you notice how every single one of those started off with delocalized electrons? Those give metals almost all of their properties. The delocalized electrons. That's what it always comes back to. All right, so with that, let's pause there because as far as I'm concerned, I'm done with metals unless you guys have any questions. Yes? The way that it would show up on a quiz or test would be which is the highest or which is the lowest. And that means metals will never be your answer because they're in the middle. They're never the highest, they're never the lowest as a generality. Like you can't generalize that they're all high or all low like you can with the other types. Okay? Yes?
This is going to be on our quiz Thursday?
Yes, this is part of the Thursday quiz. Again, it's matching metallic, ionic, and covalent. We're going to start covalent tomorrow. All right, so then with that, number 63, ion dot structure notes. Okay. So we have drawn dot structures for atoms. If you remember when we drew dot structures for atoms, we would look at the atom on the periodic table, and then we knew based on what group it was in that all the atoms in group 1 had 2 valence electrons, group 2 had 2, 13 had 3, 14 had 4, 15 had 5, 16 had 6, 17 had 7, and 18 had 8, right? We used the ones place. And then we would place our dots, one on each side until we had all sides, and then we could go back and put a second. You guys remember that? Dot structures? Okay. Today, we are not only going to learn how to know exactly how many electrons an atom would gain or lose on its way to forming an ion, but we're also going to draw a dot structure for an ion. So when you draw a dot structure for an ion, there's the same 4 basic steps that I'll take each time, and I'm going to summarize them over here in the top right, and you're going to hear me say them for every example today. Step 1, you're going to write the element symbol. Step 2, you're going to place any dots that you have to place. And normally that's where we stopped when we did it for atoms. But now for an ion, there's going to be a step 3. We are going to place our symbol and dots inside of brackets. And then step 4, outside of the brackets, we are going to write the charge of the ion. So those are the 4 steps that I'm going to be using every time to write the dot structure for an ion of an element. So here we go. Let's start first with an atom of sodium. Sodium is in group 1, so how many dots would I write for a sodium atom? 1 dot, because it's in group 1, 1 valence electron. So now, when we form ions, guys, the name of the game, it's all about octets, right? We know that's a stable arrangement of electrons. So we need to take this sodium that doesn't have a full outer shell, and we want to make it have a full outer shell. There's always 2 ways that could happen. Option 1, you can pick up enough electrons to get 8. So here, sodium, it has 1, it could pick up 7 more. That would be 8, that would be its full outer shell. But there's a second option, and that is you can actually remove the valence electrons that it already has. The idea is with Aufbau, if you were adding electrons to that shell where there was only 1, if I take that 1 away, guess what's underneath? A full shell. So by removing the valence shell, underneath you have a new energy level that's full. In the world of chemistry, gaining and losing electrons in itself, I wouldn't say one's easier or harder than the other. The issue is you want to move around the fewest number of electrons. You want to get there the fastest route possible. So with our sodium, it could pick up 7, or it could lose 1. And I just asked myself, which number is smaller, 7 or 1? 1. So guess what? That's what it does. It wants to get to an octet the shortest route. And losing 1 electron is the shortest route. Lose 1 valence electron. So that will be true for every atom in group 1. They will all lose their 1 valence electron because that's the fastest route to an octet. All right, so now I'm going to draw the dot structure for an ion. Here we go. Step 1, symbol. But now, step 2, dots. Guys, we just took 1 electron away. So how many are left on that energy level? 0. Guess what? That means you put 0 dots. That's going to be a possibility that for your dots, you could have 0, or later you're going to see you could have 8. Those are your only choices for ions. You either have 0 because you've lost your outer shell, or you have 8 because you've picked up enough to fill your outer shell. So there's nothing to write for step 2. No dots. Step 3, put the symbol in brackets. This is just the chemistry notation that everybody looking knows you're talking about an ion. In addition to the fact that it's kind of a superscript up here in the corner, we're going to put the charge. If it lost 1 electron, what would its charge be? +1. You don't have to write the 1. It's not common to write the 1. You can just put a plus sign. And there we go. That is the dot structure for an ion of sodium. Now, just because it's kind of weird, I want to throw hydrogen in here also because hydrogen only needs a duet. if hydrogen's going to form an ion, it will also lose that one valence electron. So I know you're like, oh, would it gain one or lose one? Because it only needs two. I'm just telling you, it's going to follow the same trend. So hydrogen, step 1, symbol. Step 2, dots. We have no dots. Step 3, bracket. Step 4, charge. Hydrogen would form ions with a positive 1 charge. And so from this day forward, you can now say that every element in group 1 that forms an ion would form an ion with a positive 1 charge. All of them. Potassium, rubidium, cesium. I should be able to ask you now. Anything from that group, you know it's going to form a positive 1 ion. All right, so we're going to head through all the groups now. It's going to be very repetitive. So bear with me, but we're going to hit all the examples. Let's look at group 2. We're going to look at an atom of beryllium. An atom of beryllium. As an atom from group 2, it would have 2 valence electrons. I would put those 2 dots on opposite sides. And then I play, let's make an ion. Door number 1. Would this beryllium pick up 6 electrons to have an octet? Or door number 2, is this beryllium going to lose 2 valence electrons to have an octet? It's going to lose 2. All right, losing 2, shortest route possible, which means my dot structure. Step 1, symbol. Step 2 would be dots, but we just took those 2 dots away by losing them. Step 3, stick it in brackets. And step 4, by losing 2 electrons, the charge is now positive 2, which we can generalize to every atom in group 2 that their ions would lose 2 valence electrons, and that means everything in group 2 has a positive 2 charge. Let me say one thing. Mrs. Tate, does it matter if I write 2 plus or plus 2? I'm going to tell you for high school and even a good part of college, nobody's going to care, but there technically is a way for each one. Like they mean slightly different things when you write 2 plus and plus 2, but in high school nobody cares. Okay. Yeah, that I had a feeling. Just know when I write it next to symbols, I usually do the number first and the sign second, but when I just am writing by itself and when I talk, I always say plus 2, plus 3. But nobody's going to care. That would never be a reason to mark a question wrong. All right, moving to group 13. Let's look at an atom of aluminum. An atom of aluminum, and if we were in group 13, that means we should have 3 valence electrons, 3 dots, 1 on each side. And now we play, let's make an ion. Are we going door number 1, pick up to 8, or door number 2, lose what we have? Door number 2, because losing 3 is less electrons than gaining 5. So losing 3 valence electrons, that will be true for your ions. Let's write the number. Lose 3 valence electrons for your elements in group 13 forming ions. And so writing that ion dot symbol. Step 1, symbol. Step 2, dots. No dots. Step 3, brackets. Step 4, charge. I lost 3, so that means now with 3 less electrons, there's 3 more protons. That's a positive 3 charge, which we can now generalize to elements forming ions in group 13. Hey, yeah, we skipped over the transition metals. Guys, those get weird. We don't use them a ton in this format. We could, but we got to know more information. All right, so group 14. Things are going to get a little weird in group 14. I'm going to use the atom lead, and group 14 means 4 valence electrons. And so when it comes to playing let's make an ion, now we truly have a dilemma because our options are equal. Pick up 4, lose 4. This is where context comes into play. What we're going to see is atoms from group 14 that will be forming ions are usually the metals. And we know metals tend to lose their electrons. So that's why we're going to generalize for group 14 that they are going to lose these 4 valence electrons. And you're like, but Mrs. Tate, what happens if it's not a metal? And the answer is, guys, then that's not going to come up in a question. So for example, carbon. Carbon, I can't think of an example where carbon gets involved with an ionic bond and forms an ion. Carbon just doesn't do that. Carbon does other types of bonding. So as far as you're concerned, you can say everything in group 14 is going to lose their 4 valence electrons because you would only be given things where that would be happening.
So who would they be giving 4 to?
There would what?
It's like, don't they have to give 4 to an atom? So like, who would they be giving 4 electrons to?
Oh, to itself? Yeah. I mean, the metals can get involved with nonmetals because they can form with ionic bonding, like lead and oxygen form compounds. So in that case, there is a transfer not to itself. Right? And if I just had lead atoms, that's a metallic bond. That's not an ionic bond. Like you need the metal and the non-metal. You can't have that back and forth going on.
I meant like, 'cause they have to give 1 to an atom that needs 4, right? So
In theory, yes, but we're going to see you can have different ratios. It doesn't always have to be a perfect match for the transfer. Question.
For metallic bonds, it have to be within the same metal or
It can be 2 different metals. We hit that next semester. That's a mixture. It's a solution. They're called alloys. So yeah, we group those more together in AP Chem, but for right now it's just metal atoms, but they could be the same or different metals. All right, so again, we lost 4 valence electrons, so my steps symbol, no dots, brackets, and then it would be a positive 4 charge due to the loss of 4 electrons. All right, so we're going to switch it up, but it won't be a weird situation. Let's go to group 15, and let's look at an atom of nitrogen. Now with group 15 and 5 valence electrons, this is the first time I'm going to double up. After I do 1 on each side, I'm going to get to go back and put a second on one of my sides. So there's my nitrogen with its 5 dots. And now let's make an ion. Door number 1, pick up enough electrons to make an octet. Door number 2, lose all of your electrons to make an octet. What are we doing this time? Door number 1, because the pickup in this case is only picking up 3, whereas the losing would be losing 5. 3 is less than 5. So for the first time, we're going to see a scenario where we are going to gain electrons, specifically 3 valence electrons, in order to have an octet. So that means when I go to draw my ion, after step 1, writing my symbol, step 2, my dots, guess how many dots I'm putting? 8, because I keep the original 5, and then I draw 3 extra for the 3 that we picked up. So 1, 2, 3, 4, 5, 6, 7, 8. Those are my 8 dots. And then I continue step 3, put all of that with the dots in brackets. And then step 4, if I picked up 3 electrons, what would my charge be? It's going to be a negative 3. Now you have 3 more electrons than you did when you were neutral. Negative 3 charge, which we can generalize to any atom in group 15 that is forming an ion. All right, group 16. I think we're doing oxygen. Group 16, how many dots should I put? 6 dots. 1, 2, 3, 4. There's my first 4, and then I can go back, double up, 5, 6. And in the game, let's make an ion. We picking door number 1 or door number 2? Door number 1 was always gaining to get an octet. Door number 2, losing to get an octet.
door number 1.
Door number 1. If I count it out, gaining would I only need to gain 2, but losing I'd have to lose 6. 2 is less than 6, so we are going to gain 2 valence electrons. Which means drawing my dot structure. Step 1, symbol. Step 2, dots. How many dots? 8. Remember, it's always 0 or 8. If you've picked up, it's going to be 8. If you've lost, it's going to be 0. So here's your 8 dots. Step 3, stick it all in brackets. Step 4, if I gained 2 electrons, my charge will be -2, which we can now generalize to every atom in group 16 that forms an ion. They would form ions with a -2 charge. All right, so last one, because remember, group 18 isn't going to get a part of any of the shenanigans. They already have their 8. They don't form ions. For group 17, we're going to use the atom fluorine. And fluorine from group 17 should have 7 valence electrons. And how is fluorine going to achieve its octet when it forms an ion? It's going to gain 1. Gain 1 valence electron, which means for my ion, step 1, symbol. Step 2, dots. 1, 2, 3, 4, 5, 6, 7, 8 for the original 7 plus the 1 that it gained. Step 3, brackets. Step 4, charge. You can just put a negative sign. But yes, that would mean a -1 charge for any of your halogens when they form ions. So 2 things. Number 1, I hope you noticed the statement, when they form ions. Not all atoms will form ions, and sometimes they form ions in certain cases, but they don't form ions in other cases. So this is just if we were talking about a situation where we know ionic bonding was happening and that we've made ions. Okay? All right, then that means on our periodic table, in addition to generalizing the number of valence electrons, now it's probably going to be even more important for the rest of the year that you know everything in group 1 forms ions with a +1 charge. Everything in group 2 is +2. Everything in group 13 is +3. Group 14 is +4. And then remember, it steps down -3, -2, -1, because over here these guys were gaining electrons to get their octets, and this doesn't have a charge because they don't form ions. This we use way more for the rest of the year than we do how many valence electrons they have. Right? So you'll want to get into that pattern. Okay, I do have one more thing that I want to add to these notes, but being early release Monday, we're going to get cut short. So I will start off with that, and then we'll go into our covalent bonding tomorrow. But just make sure maybe looking over notes. You got a quiz Thursday, so that's all we have heading into tonight.